In this video, we will discuss about different types of density and distribution functions, which is very important in random variables and stochastic process. And already in the previous videos, we discussed about what is density function and what is distribution function. Now I am taking distribution function and density functions based on the type of random variable. So now I am taking discrete random variable, and if the random variable is discrete random variable, we have two types of density and distribution functions. The first one is binomial probability density function or probability distribution function, and the second one is Poisson probability density function and probability distribution function. So these are the two density functions we have for discrete random variables. If the random variable is continuous random variable case, now I'm taking different types. So continuously I'm writing 1, 2, 3 like that. So under continuous random variable category, I have uniform probability density function, exponential probability density function, and the other one is Rayleigh probability density function. So now they are the 5 probability distribution functions and density functions what we have, and we need to discuss about each one by one separately. So now let us start with binomial density function. We'll start with binomial density function. Now I have one experiment. So one experiment I'm taking, and this experiment is repeated for multiple times to get exact results or getting accuracy in the results. So now I'm just assuming that this experiment has been repeated for n number of times. That is n trials I performed this event. Okay. So then for this type of experiment, the binomial density function for discrete random variable x, I'm taking as fx of equal to 0 to nk, probability of k 1 minus p whole to the power of n minus k del of x minus k. So here del represents you impulse response to indicate the distribution density function response. Okay, and here the p-value is always lies between 0 to 1, and n always starts from 1, 2, and 3, and so on. Okay, and here the quantity I am taking binomial coefficient, and this is represented as nk is equal to n minus k factorial. Okay, so this is the representation of the density function. And now if you take distribution function, simply I can replace del by unit step signal, that is u of x minus k. Okay, simply I can represent. So the distribution function is, the binomial distribution function is represented as sigma k is equal to 0 to n 1 minus p to the power of n minus k u of x minus k. This is function. Okay, and where you can use this probability distribution function, that is binomial density function or binomial distribution function, where we can use. So generally this is used in the experiments where you have experiments only 2 possible outcomes for a given trial. So for this type of applications we can use, so where we have games of chance and detection of problems in radars and solar system, like that we are going to have 2 possible outcomes for a given trial. So this is about binomial distribution function, and I told you already the total videos are only for JNTU based syllabus, so I am not taking in detail about its binomial distribution or density functions. Okay, as per JNTU syllabus I am covering the topics. So the next one is Poisson density function. Poisson density function. This is also very important density function and very nice applications we have. So now if I have one discrete random variable x, and for this discrete random variable the Poisson density function is represented as fx of x is equal to e to the power of minus b sigma k is equal to 0 to infinity b to the power of k by k factorial del of x minus k. So now here b is always greater than 0, is a real constant. It is a constant. Okay, so this is density function, and now I'm taking distribution function. K is equal to 0 to infinity b to the power of k divided by k factorial u of x minus k, and again b is greater than 0. It is represented as Poisson distribution function. Okay, so the two distribution and density functions are taken here, and where you can apply this Poisson density function, we have multiple number of applications here. So when you take multiple number of applications means here, so one, I'm taking one simple example as customer care center. So here in this customer care center, the number of telephone calls made during a period of time means, let us take from time t1 to time t2, or some 2 p.m. to 3 p.m. how many calls made. Okay, so this is one best example you can understand easily to apply Poisson density function. Or number of electrons emitted from a cathode, you can take number of electrons emitted from a cathode in a CRO in the interval of time, or number of times the waiting queue is going to be formed at the petrol station or a railway station or a theater or something else. So like this you are going to calculate. Then now, how to calculate b value here? That is the main topic. B is a constant. Okay, then how to calculate b value? So now, when you observe the examples or applications, if I have mentioned for Poisson density function, so now the Poisson density function is related to certain time duration. So if you take the first application, customer care center, so number of calls made during certain period of time, or number of electrons emitted from the cathode during certain period of time, or the chance of getting Q at the theater or at a petrol pump station or gasoline station or whatever it may be. So it is related to a certain amount of time period. Okay, so now I'm taking a time period of interest as I'm taking time period of interest as t in terms of seconds, t seconds I'm taking, and average rate of counting the items, average rate of counting, or average number of arrivals taken as lambda. So in the average number of telephone calls during time period t is taken as del lambda. Therefore, the constant b is taken as t into lambda. So this is how you can calculate b value. Okay. So this is very important to remember. So now I'm taking one simple example, very simple example. So that is the number of calls arrived at a center as taken as 200 per hour. Okay, and the time taken to attend each call is 18 seconds. So now here I'm taking at a customer care center, 200 calls are there for 1 hour, and for each call 18 seconds of time is taken. Then how to calculate b value, the constant value? Then in that situation, first you need to calculate lambda value. So what is lambda? The time duration and the number of calls arrived. So how many number of calls are there? 200 calls per hour, but the time is given in 18 seconds, so try to convert into seconds. So 200 by 60 minutes per 60 seconds. So this is in terms of second. Okay, number of calls per second. Then the given value of time is 18 seconds, so then the constant b value is equal to t lambda. So you can substitute the values, 200 by 60 into 60 into 18. So what you are going to get? Totally 1. So the beta value, the beta b value is given as 1. So here, how many number of calls are there? 200 calls per hour, and if for each call you are taking 18 seconds, so then to calculate b value, to substitute in the Poisson density function equation, we need to first calculate lambda value. So lambda is given 200 per hour, so try to convert this into seconds, and b value is given with respect to the time and average rate of calls per hour. Okay, so this is the simple example to understand the concept of Poisson density function. Okay. So now I am taking one more example here. While arrivals at a gasoline station are Poisson and occur at an average rate of 50 per hour. The station has only one gasoline pump, only one pump, and if all cars are assumed to require 1 minute to obtain fuel, what is the probability that a waiting line will occur at the pump? So this is the simple problem. So now I am taking one gasoline pump station, so where I have only single pump. Okay, so now assuming that a vehicle is coming and each vehicle is taking 1 minute time to fill, 1 minute. Okay, so now if multiple cars are arrived in this 1 minute of time, you can able to get waiting line. So this is general common sense question. So what is the probability that a waiting line will occur? When will have the line formation in the pump station? Because we have only one pump in the pump station, and each vehicle or each car is taking 1 minute of time. So the average rate of occurrence is 50 per hour. So then what is the chance of getting? So generally what is happening here, if you have multiple vehicles during 1 minute of time, okay, you are going to have queue formation of waiting line at the pump station. Okay, so now I am taking the solution for this problem. So given average rate is taken as 50 per hour, which is already given. So I'm writing this in terms of minutes. In terms of minutes, I'm taking 50 per. Okay. So then first calculate b value. Already given is the Poisson density function. So b value is required to calculate. So the average rate is represented as a into t, or you can take b is equal to lambda t. So I'm taking 50 by 60 into 1. So this is going to be 5 by 6. So the b value is given as 5 by 6. Okay. So then the probability of getting the probability of a waiting line is equal to. So now the task is to calculate, to take the mathematical form. So mathematical form is simple because a waiting line will occur if 2 or more cars arrive in 1 minute of interval, because for every vehicle to fill the petrol, we are taking 1 minute. So within 1 minute, 2 or more vehicles arrive, then there is a chance for getting Q. So then I am taking this as 1 minus fx of 1 minus fx of 0. So there is no chance to get waiting line when the number of vehicles are 0 and when the number of vehicles are 1. Okay, so then you can take this as probability of x greater than x less than 2. So this is how I can take. So x less than 2, or you can take x less than or equal to 1. No issue. X less than or equal to 1 is equal to 1. So based on this equation, I can write this as probability of x greater than 2 is equal to 1 minus probability of x less than or equal to 1. So then you can get this equation 1 minus 0. So by substituting this in the density function equation. So what is the density function equation? Already we have, what is that? So the density function equation is fx of distribution or density functions. If you observe this one, fx of x is equal to power minus b, sigma k is equal to 0 to infinity, b to the power of k by k factorial del of x minus k. If you are using distribution function, that is going to be represented as unit step function. Okay, so now you can use this equation here. So for this, you can simply take what is the value, sigma e power minus, you can simply write e power minus b sigma k is equal to 0 to 1. That is enough. 0 to 1. b to the power of k divided by k factorial u of x minus k. So simply I can write u of x minus k finally. So then by substituting the values here, 1 minus e power minus b value is, what is the b value here? Minus 5 by 6. Now I am taking k is equal 0. So b value is 5 by 6 power 0 by 0 factorial plus factorial. So then 1 minus e power minus 5 by 6. So this is going to be what? And by simplification, you can get 0.2032 value. So from this, I can conclude that a line at the pump is formed 20.32% of the time. Okay. Thank you for watching.